All right, we're going to pick up today where we left off yesterday. Just looking at continuing this idea of a limit. So as I continue to think about limits, what I'm trying to define, as we discussed yesterday, is if I'm looking at the limit L for this equation, y equals f of x, which is the blue line, then right now I'm trying to make it so that the distance between f of x and the limit, the absolute value of that, is less than epsilon, which we're equaling to 1/10 in this case. Now the 1/10, we don't know what that stands for, but that's our arbitrary number that we put in. We are saying it has to be within 1/10 of our limit. So the distance from there has to be within 1/10. So now we need to find a delta where that's going to be true. All right. Now, if I look at this, my y's are already drawn in for where it's 1/10. I have these pink lines, which represent 1/10 away from the limit. All right. So if this is 1/10 away from the limit, then I can draw vertical lines, which will tell me how far my x is away from x naught, or the point that the limit's getting close, or that your x is getting close to. Remember that this would be the limit as x approaches x naught of f of x equals L. So our y value being L here, and we're looking for how close we need to get to x naught in order to keep our y within this range. So if I'm trying to stay within this range from the pink line to the pink line, I need to figure out how far away my x would need to be to make that true. So if I just go to the upper end, which is the limit plus 1/10, that's the spot where it crosses this pink line. If I'm looking at my x values where it's minus 1/10, then to stay within that range, it would be all the way down here. Now, if you remember from yesterday, our delta has to be the same amount added and subtracted. So this distance away from x naught does not look the same to me. And even though it doesn't look the same, I need to now figure out a way to make it the same. So if I'm looking at where I would actually need to put this line, if I go with the lower limit and the upper limit, it's definitely a different distance. Like I can draw a line between here and here, and I can see that that distance is not the same as this one on the left. So which one is the right one to go with? They have to be the same distance, so we have to think about which one is going to be the right one to go with. Okay? So let's draw a distance from the limit to the left-hand side now. That distance is further than what it would be on the right-hand side. So you have to think, if I'm looking at what my delta would be, trying to figure out whether it's going to be this one or this one. Right? If I make it this one, then that means that my line will move all the way over to here. And so where it crosses is going to be up here somewhere, where it crosses f of x. That is not within this yellow range. And so my delta is not going to be this because it makes it too far out. So let's readjust this to back where it was. That's how far this is away from here. If I move my other line in from the left-hand side, closer to the x naught, then where it crosses the blue is within this yellow range. And so you see how if I move my delta closer, it's going to make everything fall within this range, and that would actually be my delta, is to move it closer than what it would have actually been on the left-hand side, because I have to make it fall within the limit range, either 1/10 above or 1/10 below. Everything outside of there is not going to work. So that's doing it with an epsilon of 1/10. And again, we're still arbitrarily picking a number. We're saying 1/10. Let's see what happens whenever we make it even closer. So this is the same graph, but now I'm doing it within epsilon equals 1/100th. So it's going to make these values for my y, it's not going to be as spread out, which means my x's are going to have to be closer to x naught. I draw my lines. That's where it would be within 1/100th above the limit, and this is where it would be within 1/100th below the limit. But again, our distances from x naught are not equal to each other. So I have to make it so that those are equal. I'm going to draw a line for my distance to here. So this is a potential delta. This could be the delta we're looking for. Or it could be going to the other side. Now, just like in the last one, if I drag this delta over to the other side, you see that this distance is too far. If I had drawn a line for that distance to our x naught and made the right side match that distance, you're going to see it makes this line to touch the blue get outside of this range. So that doesn't work. In general, we are always going to want to go with the delta that is less in order to make it work. So even though I'm cutting off some of this yellow by moving this closer, it's still within the 1/100th, and that's all that matters. It has to be close enough to the limit so that it doesn't go outside of this range of 1/100th above or 1/100th below. Example 2, testing the definition. Show that the limit as x approaches 1 of 5x minus 3 equals 2. So in order to do this, I'll give you some time to write it down. In order to do this, I need to set my x naught equal to 1. My f of x is 5x minus 3, and my L equals 2. So if I was to draw a rough graph of it, thinking about what we just did and how it compares to that, if I was to draw a rough graph of it, this would be my y-axis, this would be my x-axis, this would be my x naught at 1, then if I'm looking at 5x minus 3, say minus 3 would be down here. And I would go up 5 and over 1. Just graphing 5x minus 3. That's my f of x. So I have this line between these 2 points, like this. And then I would have this range within here, same amount above and below the line where it crosses. This being my limit in the center. So I have my limit here. This is L minus epsilon. This is L plus epsilon. And so that would be my range inside of here, within the blue. So now I need to think about, I need to come up with a delta that will make it so that for any epsilon, not like last time we did 1/10 and 1/100, now I need to do it for any epsilon. I need to come up with a formula so that I can find a delta, no matter how small or big I make that epsilon, that it's going to give me a solution for it. So we need to find for any given epsilon greater than 0, you have to find a delta, so that if x is not equal to 1, x stays within the distance of x not equal 1. So we need to set it up. If we look back at our definition from yesterday, it said that our delta had to be greater than x minus x naught, absolute value greater than 0. So we need to set it up so that we have 0 less than, and then delta in the middle. Our x naught is 1, and so it's absolute value of x minus 1. So now when we look at our epsilon, going back to that definition, it said that we had to have f of x minus the limit less than epsilon. Our limit is 2. So it's the absolute value of f of x minus 2 is less than epsilon. Our f of x is 5x minus 3. So we do absolute value of 5x minus 3 minus 2 is less than epsilon. Now we're going to solve for I'll show you how we're going to solve it. It's a little difficult to explain it for now, but we basically have to get back to where we turn this into this, so that we have an absolute value of x minus 1 in the center. so that we can find out some epsilon value, so that no matter what epsilon value we're looking for arbitrarily, we'll find a delta. So I can take what I have here, which is 5x minus 3 minus 2, and simplify it. That's going to give us 5x minus 5, absolute value, is less than epsilon. Now, when I look at this 5x minus 5, I can factor out a 5 because there's a 5 in both of these terms. So when I factor out a 5, it pulls it out in front of the absolute values, and that's x minus 1 inside the absolute values, less than epsilon. Now, oh my gosh, what is happening? Now whenever I look at this x minus 1 is the same as our delta up there. But I still have the 5 on the outside. It's 5 times all of this. So we're going to divide by 5 to make this the same. Divide by 5 and get absolute value of x minus 1 is less than epsilon over 5. Up here, this looks exactly the same, which tells me that my delta is just epsilon over 5. That's what I was looking for, was finding a delta for any epsilon. So that's our solution. That tells us that no matter how big I set this margin as, going up and down, no matter how big I make that, I can make it so small or so large, all I'll ever have to do in order to find where it falls within these limits is do our x naught, 1 minus epsilon over 5, or 1 plus epsilon over 5. And every time it will make it fall within this range. So I can choose any random number for epsilon now, and then all I have to do is do that number divided by 5, subtract that from 1, and add it to 1, and it will fall within this range here. Questions? When you do these problems, you will not have to use the graph. I'm just trying to show you a visual representation with the graph, and I realize it can make it more confusing in some cases, especially if you're trying to draw the graph for some crazy functions. It'll make it hard. Okay, so basically this whole thing here is, in words, what we just did. So to algebraically find a delta for a given function, limit in x naught, we can accomplish it in 2 steps. So first we solve the inequality, f of x minus L less than epsilon, to find an open interval from A to B containing x naught on which the inequality holds for all x naught equals 0. Sorry, x equals x naught. Then find a value of delta that's greater than 0 that puts the open interval x naught minus delta and x naught plus delta centered at x naught inside the interval for the limits, so that the inequality holds for every x in the interval. Finding deltas for given epsilons. For the limit as x approaches 5 of the square root of x minus 1 equals 2, find a delta greater than 0 that works for epsilon equals 1. So we have to find a delta greater than 0 such that for all x, I have absolute value of x minus 5 less than delta, then this has to be less than 1. So because this is giving me an epsilon, and I don't just have a random one, we can do our 2 steps that we just went through. So the first thing that I have to do is look at this. This 1 here in the inequality is my epsilon. Then I would just solve this inequality and see what x is. So, when I solve the inequality, the first thing that I'm going to do, because I'm given an epsilon, is I'm going to get rid of my absolute values. And that's going to be the square root of x minus 1 minus 2 is less than 1. Whenever I get rid of the absolute values, it means that I also have to consider the negative possibility. So it's also greater than negative 1. Now I'm just going to solve for x. So in order to do that, I'm going to add 2. Whatever I do to the middle, I have to do on the ends as well, both sides. So that gives me the square root of x minus 1 is less than 3, and then negative 1 plus 2 is 1. Now I have to get rid of the square root. In order to do that, I square it, which means I square both of those. 1 squared is 1. Then I add 1 to get rid of it. It gives me 2 is less than x is less than 10. Which means my original inequality, this thing up here, is true for every value between 2 and 10. So my open interval would be from 2 to 10. And those are my x values that make this true. Okay? Because I'm looking at my limit as x approaches 5, I need to find a delta that's going to hold true. So if you remember the graphs that we were originally doing, I need the endpoint that's closest to 5. Which endpoint is closest to 5? 2 or 10? Two is closer. How would I get to 2 from 5? I would have to go down how many? 3. That tells me that my delta is 3. Because 2 is 3 units away from 5. So when I rewrite this inequality now, it's going to be 0 is less than absolute value of x minus 5 less than 3, because delta equals 3. Make sense?